Okay, so Simon mentioned that there was an announcement from the university which says we shouldn't have any lectures next week. I think that's because of COVID-19 is spreading inside the campus. So yeah, we are not going to have any lectures next week, and I think because our schedule is reasonably flexible, I think it shouldn't cause any problem for the kind of things that we want to do throughout the course. Okay, so there won't be any lecture on Monday and on Tuesday next week because of Chuseok holiday, and there won't be any lecture on Thursday because of the policy imposed by the university. Okay, so let's get started. And here's where we are. So we are in the middle of discussing chapter 3. So let me change a little bit. So chapter 3, which is about Rademacher complexity. This is better. And then growth function and VC dimension. So they are all measures of complexity of a hypothesis class, which can be applied when hypothesis class is even infinite. Okay. So these are the things that we are talking about. So these are the things that we talked about. So what we did last time. So we talked, so here's a quick review. So we talked about Rademacher complexity. And then we define something, initially we defined something called empirical Rademacher complexity, or set of function class F. Then we defined the Rademacher complexity as an expectation of size M of F. This means it's an expectation of empirical Rademacher complexity. And what was the empirical Rademacher complexity? This is really saying whenever randomly, so whenever we choose direction randomly, can we point to the same direction using some functions in F with respect to the inputs specified by S. So if S is sequence of input from U1 to UM, it's defined to be supremum. So actually no. There's an expectation over Rademacher variable, which are uniform random variable on -1 and +1, so M dimensions. So essentially, we are selecting random direction, and then see that whether we can align or we can point to the random direction using some function F that apply to input U1 to UN. So supremum of F such that 1 to M sigma I and F of X sigma UI. That's how it's defined. Then the reason we are interested in this concept, I think the definition of Rademacher complexity, it captures intuitively how rich the function class F is. At the same time, it has a lot of symmetries, which allows us to come up with some nice results about involving Rademacher complexity. So the particular theorem that we proved last time, in the middle of proving last time, was theorem. It was called 3.3. Theorem 3.3, and the theorem say the following. if we have a function class f, which is a mapping from U to bounded range 0 and 1. So this bounded range is really important because that bounded range is the one that allows us to use concentration inequality. In this specific case, we use so-called McDiarmid inequality, and that's applicable only when we have a function class of the bounded range. So if you consider a function class with unbounded range, things start to become much more difficult. So if that is the case, and then if we have some precision requirement, delta, and some m for the number of samples, and also some distribution on the input. See? So then the result say the following. For any m independent samples from S, for every function f. What we want to say is we want to measure, or we want to bound expectation of f when input is give samples from the distribution D. But we cannot really do it. So what we want to do instead is we want to have an empirical estimate of the bound. That is what's written on the right, what I'm writing right now. So it's a sample from empirical distribution, which is a uniform distribution over S. And we compute expectation with respect to this. Because S is finite, this is just an average of F applied to every element in S. So S is U1 up to UN. And then, but if we just say they are equal, that's always wrong. And we want to put some slack. That slack is going to put something extra. We're going to put it here. And that slack consists of two parts. One is coming from Rademacher complexity that allows us to have the uniform bounds, which works for every function f, small f in the function class capital F. And then there is another quantity that's coming from essentially the application of concentration inequality, which is really coming from the estimation error. And this part was 2m log 1 over delta. And then we said this type of upper bound uniformly holds for f with high probability, that is 1 minus delta. So that's the one result. And then the second result is we can have something very similar. But with something where the right-hand side of this inequality has quantity that we can actually measure in most cases. So, I mean, the one, I'm going to explain why the one below is actually useful. So we have here two empirical Rademacher complexity with F. And then 3 times 2m log 2 delta 1 minus delta. Okay, compared to before, we'll compare these two. And both the one above give the upper bounds, which is quite useful when we do theoretical analysis. But for practice, if we want to really measure compute the upper bound, we are in trouble because this Rademacher complexity of the function class f is defined with respect to distribution D, which we don't know. I mean, that's the purpose of the learning is to figure out, get some information about this this distribution D and do something about it. So that distribution D is something we don't know. Instead, the quantity that below is only consists of something we all know. So we know the function class f. We also know the samples, which is in the capital S. So the quantity below consists of everything, the things that we consists of only those things that we know. So that in theory, we can compute the quantity of this upper bound on the second statement. And so that's why the second statement is useful. On the other hand, nothing is for free, so we have to pay some price somewhere. The price is, roughly speaking, we are estimating Rademacher complexity by empirical Rademacher complexity and the upper bound, uniform upper bound below. So we pay the price. The first price is the second term has this constant 3. That means essentially we are adding 2 more of the term above. The second, instead of 1 over delta, we have a 2 over delta, which means we are really using the one above with instead of using delta, we are using delta over 2. And then we kind of using concentration bound twice with the delta over 2. So that you can see in the proof that I'm gonna just show you now. Now for the proof of this statement, we use the McDiarmid inequality, but it has 2 steps. The proof has 2 steps, but then the key quantity that we compute in the proof is this, what we call function phi. That's applied. We apply to this S, which is a sequence of examples defined as a supremum of F, where the real quantity that we care about, which is a real expectation, how much larger that real expected. The maximum difference between the real expectation and estimated expectation. And this appears naturally because we are looking for the uniform bound. So the supremum here is really saying we are interested in the uniform upper bound. So then this is the quantity, and the proof consists of 2 parts. The proof of this one, the first statement, consists of 2 parts. The first part was to show that P of S, and we compare P of S with its average. Okay, so its average is expectation, where S is a sample from D of M. So if you prefer, we can put S prime to distinguish this. So we want to say, okay, can we somehow upper bound using expectation? It turns out that's possible. And as long as we put some select here, so that select is 1 over delta. And this holds, this upper bound holds with probability at least 1 minus delta. And as I said, this can be proved by concentration inequality called McDiarmid inequality. And then the proof of that crucially use the fact that we have this bound, all of our functions are bounded. Okay? And we just based on that information, if all of the functions are bounded, and that implies our function phi is also bounded with respect to a single coordinate change. So if we just change it in the parameter S, if we just pick one of ui and then change the ui to something different, the maximum difference is bounded by 1 over m. And that is what enables us to use concentration. That plus S is independent samples, it consists of sequence of independent samples. These 2 allows us to apply the concentration inequality. Okay, so right, that's the first thing we prove. The second thing we prove is something that's not probabilistic bound. It's just something that's always true. That always true. This bound is always true. Is that expectation of P of S prime is bounded by 2 times Rademacher complexity over the function class. And I showed you the derivation last time. The derivation uses the symmetries of the definition of Rademacher complexity. So many distributions are invariant with respect to certain change, and we are exploiting this, the invariant property of the distribution to obtain this upper bound. So concentration inequality for number 1, symmetries for number 2. If we do so, then we can replace just some yellow color here. Yeah, we can replace this part by 2 times Rademacher complexity. That gives us the upper bound claimed in the equation 1 directly. Now, how can we get the second one? For the second, we're gonna use something very similar, okay? So what we will do, so the change that we will do is that we will show, maybe we essentially repeat the proof in number 1, but instead of with probability delta, okay. We do the with probability delta over 2. So if delta is like a 0.1, we only put, so delta is like our budget. So we are using half of our budget to get on the first upper bound. So if we use delta over 2, then this part will also change. And that change, the part will be 2 over delta. So you can kind of see that where this 2 over delta in below coming from. Okay. So that's one thing we're gonna do. So we said with so that's it. I mean, this if you subtract delta over 2, that's a higher probability than subtracting 1 over delta. So we ensure number 1 holds a bit higher probability. Okay, so that we have some rooms to play with, and that extra room we exploit it to show the third fact. So the third fact is R M of F is going to be bounded by R over M of F is going to be bounded by empirical Rademacher complexity over S together with square root of 2m 1 over delta. This holds with probability 1 minus delta over 2. This is again can be proved by applying McDiarmid inequality. So this time, the McDiarmid inequality say we have a collection of independent random variables. There is some function applied to the collection of independent random variables. So in this time, when you apply the McDiarmid inequality, the specific function that we are using is this following function, which is thinking about functions that maps this set of sequence of right. So function that maps input S, so which is a sequence of examples, to empirical Rademacher complexity. So this is a function. If we give a sequence of examples, this written as S, which is U1 up to UN, then we can compute the empirical Rademacher complexity. And then the right-hand side that you see here, that's an expectation of the quantity that we care about. So, I mean, it's not written exactly the same form as number 1. This concentration inequality tells us, I mean, the relationship between the between the expectations and the estimate, and then if you just apply McDiarmid inequality with this specific function, this is the quantity that we can get. Also, just like before, what's important here is that the empirical Rademacher complexity has some boundedness property, and that's crucially exploited here. Now, if you combine this 1, 2, 3, and that gives us the bound below. So we start with number 1, that gives us the V of S. And then now using number 2, we replace this expectation by the one below, and we use number 3 so that we replace this 2 times Rademacher complexity by 2 times empirical Rademacher complexity and 2 times the quantity below. So then we get a lower bound. And all these things can be put together by so-called union bound. So that's I'm going to mention this a little bit, and then so 1, 2, 3 can be combined by union bound to give number 2. And what does that mean by union bound? Really, this union bound statement goes like this. So if you have a probability of a certain statement, let's call it a statement, use a phi. So phi can be a statement like this, something is upper bounded, but that's a probability is at least 1 minus delta 1. And then probability of, let's call it P1, P2 is also at least 1 minus delta 2. And we may ask, what's going to be the probability of P1 and P2? Can we put some lower bound about this? It turns out that it's possible. That lower bound is 1 minus delta 1 plus delta 2. The one way to think about it is that there is a delta 1 chance at most, P1 break. There is a delta 2 chance at most, P2 break. So in order for P1 and P2 break, either P1 should be wrong or P2 should be wrong. And each of the probabilities bounded by delta 1 or delta 2. So if you just put those probabilities together, then we'll cover the cases where the P1 and P2 will fail. I mean, you can prove this very easily by, some simple fact about probability, but this is a statement that we're going to use over and over again. So this really say we have one fact with high probability, another fact with a high probability. How can we combine them together? And the answer is yes. And then we can get the high probability lower bound with the further conjunction. Okay. So in our specific example, delta 1 is delta over 2. It is not max, it's just delta 1 and delta 2. That's because this is really coming from union bound. So maximum, that is a delta 1 plus delta 2. So we have a delta over 2 that's coming from the number 1, delta over 2 coming from number 3. So that's why we do this management. So now coming back to the second statement, we can see that now we obtain the second statement. It's a second statement from the first with a bit tighter bound. So that's why I said we are using this 2 over delta here. And also we are using this type of probabilistic statement twice. And one for the number 1, the first statement. And then the other is for this, to estimate this Rademacher complexity. And because the 2 appears in the above, that's why we have a number 3. So this term coming twice, but in the second occurrence of this term, it gets multiplied by 2. So that's why we have a number 3. Okay, so that's a reminder and the completion of the Rademacher complexity, the general result of Rademacher complexity. So now we're gonna use it to our setup. So we set up. So how does it apply? And in our setup, we're gonna instantiate the previous result. So what's our setup? The setup goes like this. So the U that I wrote before is going to be the input times output. Okay, in our setup, we will use a specific output Y, which is going to be -1 and +1. It can be 0 and 1. You can adjust the result, but -1 +1 turn out to be extreme. It's very useful to simplify the calculation. So that's our setting. And then we may, in our setting, so we also have a set of hypotheses. So hypothesis set that's going to be a mapping from X to Y. So it's not exactly the function class f, the curly f that I wrote. So what is f in our setup? So f is going to be a mapping. It should be a mapping from set of maps from U to, especially if you want to use the previous result. Make it more explicit. U is x times y, so it has to be x times y to 0 and 1. So what kind of f we're gonna use? This f, in our case, in the textbook it's written as a g, but I'm gonna continue to use this f because that's the symbol that I use. It's really composition of this function from one hypothesis together with a loss function. So you take x and y, and then you map h, you pick some h and then map h to x, but then it computes its loss, which means that assuming y is the right input. So h is, so it's really take for given h, and whenever somebody give me xy pair, which is the input together with the desired output, that what we are computing is a loss of the function h with respect to that specific input output pair. So that's what this induced function class f is. Because of this indicator function, so see that because of this indicator function, the value is always between, I mean, it's either 0 or 1. So it's satisfied this range requirement 0 and 1. Now one interesting thing here is that if you take function f in this set, so let's pick some function f here. Then if we compute, it's expect. So okay, let's pick some distribution d over x and y. And what this distribution is really correspond to the stochastic setup or stochastic scenario that I explained at the end of the chapter 2. So this stochastic setup really is a distribution over inputs and the corresponding the desired output. But unlike the deterministic setup where we have a definite the output per each input, our output may be a bit noisy, but that desired output may be not precise. It may be there is a little bit of fuzziness, and that's captured by this distribution D. Okay. So then in that setting, let's think about for F, we compute the expectation because that's the quantity that appears in our previous result. X and Y. But this expectation is really expectation of xy of this error of h of x not equal to y. And then that is exactly the definition of risk in the stochastic setting of function h. Okay. So this quantity that we talked about in our previous theorem is exactly the risk that we are talking about here. The same way, the empirical risk, the xy from empirical distribution over S. So S is now just a sequence of X, is a sequence of XY pairs. Then in our theorem, we talked about this. Okay, so that is, when we expand the definition, it's 1 over m. Summation of I is equal to 1 to m of h of xi is not equal to yi. That is exactly empirical risk. Empirical risk of h. So what does this mean? Now we using these observations, let's rewrite the conclusion of the previous theorem. The conclusion of the previous theorem say the following. The number 1 said, so I will use this form with probability at least 1 minus delta. The previous theorem now said let's use blue color because I mean this quantity is going to be bounded by this quantity plus some extra terms with high probability. So with probability 1 minus delta. So what are they? So the quantity, the expectation, we can write it as risk without probability, and the following holds. Say for H in H. For F in this curly F is exactly the same as for H in H, and then we are thinking about the function below. Okay, so then the function below, the functions, and then if you compute the expectation, that is going to be R of H, going to be bound by R S of H. So risk of H is going to be bound by empirical risk of H plus 2 times Rademacher complexity over function F, the set of the function class at this curly F plus square root of 2m log 1 over delta. So that was our first statement. So then that give looks like it's kind of the shape that we want. Okay, we want to have a bound, uniform bound for risk in terms of empirical risk. So things are pretty close to what we want, except that there's just some annoying term. I mean, this is not exactly the Rademacher complexity of F. Yeah, it's related to perhaps some complexity of our hypothesis set H, but it's a bit indirect. We want to rephrase it in terms of maybe Rademacher complexity of H or something else, something more directly related to H. Same way, our second statement, minus delta. It looks like this for H in H. R of H bound by the empirical risk of H plus 2 times empirical Rademacher complexity of S. So this is a probability both over sample from the M. Same thing should go here. And but just 3 times square root of 2m log 2 over delta. So again, if you look at the statement below, the unknowing term is, I didn't quite write it fully, has to be F. So the question becomes, can we somehow rewrite the Rademacher complexity of curly F, perhaps by Rademacher complexity over H, because that's the one that we are dealing with. Turns out the answer is yes. So that's the lemma 3.4. So in the setting that I described so far, which is output is between -1 and +1, and so the setting of this number 1, the following is true for any sequence of examples, which is input-output pairs. We have this empirical Rademacher complexity of this function class F is bounded by above by 1/2, and empirical Rademacher complexity of H. But here, when we talk about this S, we are restricting, we are taking only the X projection. So where S of X is really, it's just taking X1, Xn, or when we write S as X1, Y1, Xn, Y1. In other words, it's a projection of the first component, the first part of the pair, for every pairs in the capital S. Okay. So that's the relationship. So before proving this relationship, let's see what can then we say. This relationship means that we can replace, so that relationship is just true all the time. It's not a probabilistic fact. For any S, that's true. So for any S, this is true. So which means that now if we use this fact, then we can replace the one above this entire term by, so 2 times Rm of F can be replaced by Rm of H. Okay. So one thing I quite didn't say is, if this is true, that first implies for any M, the Rademacher complexity of F is bounded by 1/2 and Rademacher complexity of H. That's assuming the expect distribution that we are using on this hypothesis set is the one induced from so we have a distribution here that's on the input and output, and that distribution, if you marginalize out the output part, then it induces the distribution on X, which is a probability distribution on X. So Rademacher complexity here is computed with respect to this induced distribution. Here it's computed with respect to D. And that's true because if you just take expectation on both sides of this inequality, you can get 1 below. Okay. So that means we can replace in the term that I just pointed out by this quantity that I just wrote there. And in a similar way, we can replace this empirical Rademacher complexity involving F by just 2 times empirical Rademacher complexity involving F by just Rademacher complexity of H with the projected part of S. Okay. So that gives the result. If it's just a replacement, what I just described to you, here the upper bound that I just described to you, that's the result called theorem 3.5. So they say, and with high probability, for all h, the risk is bounded by empirical risk plus not 2 times, but just the Rademacher complexity of hypothesis set H. So as I said here, we are using this distribution induced on X time plus this extra quantity. And the one below say the same thing with high probability. For all H, the risk is bounded by empirical risk plus not 2 times, but just empirical Rademacher complexity of H with respect to this X projected S plus 3 times this quantity. Okay, so that's what the theorem 3.5 said. So it allows us to, so it has a statement that expresses the type of bound just involving the Rademacher complexity of our hypothesis set. So that's the quantity that we care about. That they're more directly related to what we care about. So now the question becomes, how can you prove the lemma 3.4? The proof is not very difficult. So the proof of lemma 3.4, it's, in some sense, it's a calculation. So, and really this 1/2 is coming from the fact that every function has every functions in this curly f has a range between 0 and 1, but the function in H can be between -1 and +1. It has a bit larger range, and that's a bit related to the why we have a 1/2. Let me just write the proof. So if you compute this, expand the definition, that is saying the following. So Rademacher variables, so uniform -1 and +1, and a little bit. Such supremum of f in f 1/m summation I is equal to 1 to m sigma I f of xi yi. That's just the definition, and here xi using convention s is x1, y1, etc. m, yn. Okay, so then, and if we expand the definition of f, that is, this part becomes the same as sigma I. So first, my proof is very dirty, but so this part, because every function f is coming from H, it can be written as place like this. This part can be replaced by sigma I indicator H of xi different from yi. Key trick in the proof is we write this indicator function as follows. Because H of xi have a +1 and -1, here's what you can do. It's 2, 1 minus H of xi yi. So if xi, the h of xi, yi are the same, they will be either both +1 or both -1. And this, the quantity that I just wrote is going to be 0. So the entire thing will be 0. And that's exactly same as what we started with. If they are different, this multiplied term is going to be -1. So then 1 minus -1 is going to be 2. Divided by 2 is going to be 1. So this whole thing will become equal to sigma I. So this equality is true. So it's a bit like encoding of indicator function using just multiplication and division and so on. Now, if after this, now we continue our calculation. So if you continue the calculation, the expectation becomes expectation over sigma. So because, okay, just write it here, supremum of h 1 over m, sigma I is equal to 1 through m, and then sigma I divided by 2 minus 1 over m, sigma I is equal to 1 through m, sigma I, just put it there, minus sigma I yi h of xi. Now, you see this term, it has nothing to do with h, so it can be taken out from the supremum. Then also sigma I has a half and half probability for being +1 and -1. So it turns out the expectation of what I just highlighted in this part is going to be 0. So what this means is it's going to be same as 1 over half. Only the second term survives. And then supremum of h 1 over m nation equal to 1 through m minus sigma I times h of xi. So here we are using symmetry again. So we have Rademacher variable and y1 up to ym are fixed. It's a fixed either +1 and -1. But this multiplying all these sigma with this yi, we are not going to change any their distribution. So here's what I mean precisely. So here what we note that sigma 1 up to sigma m, they are random variables, uniform random between -1 and +1 for all the m variables. Then if you compare minus yi, sigma, sigma 1, 2, minus ym, sigma m. I mean, these two guys have a same distribution. I mean, this notation means equal in distribution, same distribution. That's because for uniform distribution, if you multiply fixed plus and minus sign, that's not going to change anything because so they have the same uniform distribution. So in other words, because uniform distribution has many interesting symmetries, so just multiplying fixed signs there is not going to change anything. So that means the one that I just wrote there is the same as following. So let me use this. So this thing is same as 1 over 2. It's supremum of h 1 over m sigma I from 1 to m, and can just write this sigma I h of xi because of the equality between two distributions. So that's exactly Rademacher complexity. Rademacher complexity of S of x part empirical Rademacher complexity over H. So a statement that we want to prove here. Okay. So the key step of this proof is the use of use of this trick. So and then the use of this trick, because it involves 1 over half, so that's why we have in the statement we have a 1 over half there. So we have 1 over half that's coming from this 1 over half that exists here. Okay, so just okay, so then now so that concludes our discussion of the Rademacher complexity. The real bound that we care about is this one with the form here and given here. So with high probability, the risk is bounded by empirical risk plus Rademacher complexity of a hypothesis set plus this extra term. Also with high probability for H, the risk is bound by empirical risk and empirical Rademacher complexity, and plus this the terms which have a 3 and the 2 over delta compared to the one before. I don't expect you to remember this, but I hope you get some idea. So that's actually quite simple. So let's move to the next slide. So Rong's question, I think if you think about the two Rademacher variable, so I think the best way to understand it is an example. Two Rademacher, sigma 1, sigma 2. It's a uniform distribution of plus 1, minus 1, right? Plus 1, minus 1, plus 1, plus 1, and plus 1, and minus 1, minus 1. So there's a probability of all this. But if you just say multiply just minus, so y1, suppose y1 is 1, y2 is minus 1. So then think about this minus y1 times sigma 1 minus y2 times sigma 2. So then what are we gonna get? So the first guy will be transformed to, this minus y1 is just minus 1. This is equal to 1. So first guy will be transformed to minus 1 and minus 1. Second guy will be transformed to minus 1 and plus 1. Third, plus 1, plus 1. Fourth one, plus 1, minus 1. Then you can see that it's going to be the uniform distribution. The reason is really that we are here, what we are doing is we are defining a map that takes this Boolean value, B1 and B2, and we map it to the value minus y1 times b1 minus y2 times b2. And this function is bijective. And any bijective map on the uniform distributions, it's going to induce the uniform distribution again. Okay. So for the discrete domain. So that's why, it doesn't change the distribution. So you can do the calculation, or you can think of it this way. Okay, so erase. So now let's move to the next part. So the next part is Rademacher complexity. So now we're gonna introduce something called growth function. That's a third point. But to see the need of the growth function, it may be worth just remembering what we have just proved so far. I think my color was green. Sorry about this. Okay, just use one highlight. So you want to think about growth function. And then the Rademacher complex, the complexity bound was like this. We have, so with probability, the first complexity bound, that's what we care about here. For hypothesis H, risk is bounded by empirical risk plus Rademacher complexity over H plus 2m log 1 over delta. But now what's the problem? The problem is this Rademacher complexity is quite hard to compute, even when you know the distribution. Okay. Also, often we don't know the distribution at all. So what we want is, even when you know the distribution, it's hard to compute. So I think later I will upload my lecture notes, and then you will see that depending on the distribution, actually this Rademacher complexity changes quite a bit. So it's a bit tricky quantity to deal with. So what we are aiming at using growth function and VC dimension is something which is less informative than this Rademacher complexity, but easier to deal with. So I already mentioned to you that by less informative, we mean that we want a quantity that does not depend on the distribution. We are losing something, but then in gaining, what we're gaining is easier to deal with. So that's what we want to get. So growth function is one example, which has informations more than what we call VC dimension. Okay. And VC dimension loses more information, but it becomes much easier to deal with. So what's the definition of growth function? Quite simple. So definition 3.6. So the growth functions so it depending on our hypothesis set, it's a mapping from natural number to natural number. Actually, natural number plus infinity for hypothesis set. So all the hypothesis set or function class will be assumed non-empty. So H is defined by I H of, if we take the integer m, that's a supremum of 4x1 to xn in the inputs, such that input for which the cardinality of this get maximized. H of x1 to H of xn. So I think if you just look at, so what I mean, intuitively what it means is we can pick any input. So, and then for that input, we are applying this H to all those inputs. Okay, to all those inputs. So then because there are m inputs, it will produce m-dimensional vector. And then we just collect how many different m-dimensional vectors we can have. Now consider the extreme scenario where our hypothesis that H has only one function. So then whichever input we give, we have our hypothesis that has only one function, and then in particular that one function is a constant function. It always returns 1. So then this m-dimensional vector is going to be a vector which consists of only ones. Okay, there's going to be only one constant vector. So this growth function is going to be defined by just 1. Okay, but if our hypothesis set is rich, so it contains lots of functions, and also each function is interesting. It maps inputs to some interesting outputs. I mean, the different inputs to the different output likely. So then this growth function will become quite large. So in some cases, it can be an infinite. Now, in the typical application we are thinking about, so definition of growth function. So in our typical applications, we are using the growth function with a particular setup where H is a mapping from input to -1 and +1. So that's a setup that we have been using so far, -1 and +1. Now, in this setup, actually the growth function is bounded, and then the bound can be computed like this. So in this setting, because for each output, it's either -1 and +1, the maximum that we can achieve is bounded by 2 to the n. So if we have m inputs, and for each of the inputs, we can have either -1 and +1. So if our hypothesis set is very rich, then we will be able to produce all the possible -1 and +1 combinations. So that's going to be equal to 2 to the m. Otherwise, it's going to be smaller than 2 to the m. And 2 to the m is going to be an upper bound in this setting. So in this setting, one measure that you can see is if these growth functions, when m gets larger, the growth function will become larger. It's a monotone function with respect to input. But the maximum it can have is a 2 to the m. But then if our hypothesis set is not very rich, at a certain point, we start to deviate, where we start to get smaller than this exponential function 2 to the m. Okay, and by looking at this deviation patterns, we can get an idea that how complex, how rich our hypothesis set is. Okay. Now, here's some. So then the next question is, okay, this growth function seems to measure the complexity or expressiveness of a hypothesis set. How is it going to be related to the Rademacher complexity? Well, can we somehow use these growth functions to obtain a bound? Okay. To obtain a bound like the one before, but instead of this Rademacher complexity there, can we replace this Rademacher complexity by this growth function? It turns out the answer is yes. And here's some key lemma, and let me just show you the key lemma and then show you the conclusion first. And maybe next time we prove the lemma. So the key lemma is called Massad lemma. So lemma is called. I think the better way to do this is to just give you the conclusion first. So the conclusion is theorem 3.9. Okay, we just write the corollary first. Corollary 3.8. That corollary say the following. So if you pick any so pick M and also any distribution on the input, so that we can talk about Rademacher complexity. And so this is a setup where our hypothesis set, I mean, the things that we are using from the input, the up -1 and +1. In this setting, then we can show the Rademacher complexity of a hypothesis set is bounded by square root of 2 log growth function and m. And so it's going to be bounded by the quantity like the one here. Now we can use this corollary to prove the kind of bound that we care about. The kind of bound is theorem 3.9, where we replace Rademacher complexity by the growth function. So let's say for all distribution D, I mean, this time we are talking about the input and output distribution. So it's a bit confusing. D is used sometimes for distribution on input, sometimes distribution for output. I hope that you can distinguish them. For distribution on input output, in other words, for any learning problem, for any required precision, what we have is with probability, at least 1 over delta over a sample which is independently sample, is a sequence of input outputs, independent sample from M. We have the following statement is true. For every hypothesis, the risk of H is going to be bounded by empirical risk of H plus, instead of Rademacher complexity, we have the quantity that we given here, M 2 log growth function plus 2M log 1 over delta. So that's the statement. Now let's think about the worst case scenario. What's the worst case scenario? The worst case, and then the worst case scenario in this bound that I described to you is going to be meaningless. I mean, this bound start to make sense or say something interesting when our hypothesis is that it's not so complicated. It has some regularities. It's super complicated. So then this bound that I described to you won't say anything. Okay, just use. So this bound, this is not going to say anything. So what's the worst case scenario? The worst case scenario is the following. So it's like, I mean, so some examples. So the example is, what's the worst case scenario? Worst case scenario is growth function grows very fast all the time, which means that this is equal to 2 to the n. So then what we can have, I mean, we can have that the quantity here is going to be, I mean, there are some constants, But if you take, well, now you can just write it exactly. It's a 2m log 2 divided by m. So it cancels, it's a 2 times log 2, which will be perhaps greater than 1. I think that's the case, but I didn't calculate this. So this is now going to be, I mean, it's quite close to 1, at least. So now if you plug in this quantity, which is highly close to 1, to here, so then it will say that our risk is bounded by empirical risk plus 1 plus something, but the maximum a risk can have is equal to 1. Okay, it's an expectation of some function which have a maximum value is equal to 1. So this bound will be meaningless. It just said some risk is smaller than equal to 1, which is always true. So this bound is meaningless. And that's expected because, I mean, we can get some meaningful bounds only when the hypothesis set is somehow constrained. If it's not constrained and can be anything, then we don't expect to get any meaningful bounds, and that's what's going on here. Okay, so I'm gonna stop here today, and as I said in the beginning of today's lecture, there will be no lecture next Thursday. So next week, I mean, you can relax and you can just have fun. So we are not going to have any lectures at all. Okay, and then I will see you again on not next week, but 1 week after. Okay, so that's it for today, and I hope to see you again later.